All right, so we are going to attempt some homework problems for section 1.1 on what we just learned about atoms and subatomic particles. So what I hope to do here is I hope to read the question, and for all you watching at home, pause the video and attempt the question that we are on, and then unpause the video and hear my explanation. We will go through the first couple questions and leave a few of these for homework, and I will use that to gauge your participation for today. And you'll actually end up getting a grade for some of these questions. So we will start off here. So if you know the atomic number and the mass number of a neutral atom, first off, let's define, or better define, what neutral means. So if you recall from the notes above, a neutral atom indicates that the number of protons is equal to the number of electrons. So from a charge standpoint, protons have a positive charge and electrons have a negative charge. So if you have the same number of each, those cancel out, and the result is a charge of 0 on a neutral atom. So given this information today, right here, we know that the atomic number, so what is the atomic number here? That is the number of protons and the mass number. And if you recall from the definitions above, the mass number is the number of protons plus the number of neutrons. So I'll just bold these so they stand out a bit. How can we use this information to determine how many electrons are in the atom? So the place where we mention electrons up here, basically saying in a neutral atom, the number of protons equals the number of electrons. So if you know the atomic number, or if you know the number of protons, you could easily guess how many electrons there are. So in our answer here, we'll write, in a neutral atom, the number of protons equals the number of electrons. Since we know the atomic number, we know the number of electrons. So for instance, because they want us to give a specific example here, in a neutral carbon atom, only I could spell today. In a neutral carbon atom, there are 6 protons and 6 electrons. So that kind of summarizes our answer here for A. So now moving on to B, how can you use this information to determine how many neutrons are in the atom? So when you see neutrons, you want to start thinking intuitively about mass. So for neutrons, we know that the mass number, right? We know that the mass number is equal to the number of protons plus the number of neutrons. So, and in this little equation we have set up here, we are already aware of the mass number and we are already aware of the protons. So in order to figure out how many neutrons there are, we would just subtract the number of protons from the mass number. And then a specific example here, carbon with a mass of 12 minus 6 protons equals 6 neutrons. Carbon's my favorite element to use in these examples because it's easy and most people are familiar with it. But feel free to get creative if you'd like. How can you use this information and a periodic table to determine which element you are dealing with? Illustrate using a specific example. So if we're looking at, and we could use this periodic table here, I've also got a copy downloaded. So here, we know that the periodic table is sorted by atomic number. So it starts low, right? Hydrogen has an atomic number or 1 proton, atomic number of 1. And you read it like a book. So as you read left to right and down each row, there's a slow increase in the atomic number as well as the mass in most cases. So based on this information, what the question is asking us, how do I pick up the question? How can you use this information and a periodic table to determine which element you are dealing with? So if you know the atomic number, right, that essentially tells you where to look on the periodic table. And that's the most straightforward answer that you can use here. Say the periodic table is sorted by atomic number. Knowing the atomic number of the atom allows us to find it. And I'll actually say atomic number of the element, just because the element is referring to the specific atom. So that's our first 3 questions here, some really good review of the vocabulary that we touched on in the notes. If you are struggling with this in any way, don't worry. I know it's a lot to process at first. Just definitely feel free to ask questions or write on the discussion board if you ever feel stuck. And this next question will actually be a very good review. This will really tell you if you know it or you don't, right? Because we're looking for specific numbers in these empty boxes on the table. So if you find that you're struggling with this table, definitely reach out for help. So they essentially give us part of the puzzle for each row of this table, and they want us to fill in the rest. So we start with that isotopic notation. So if you'll recall, we've got the atomic symbol, we've got the atomic number in the lower left, the mass number in the top left, and sometimes there's a charge here in the top right corner. However, here there is not, because here we are assuming all atoms are neutral. And just in case you need that reminder, and it's totally okay to write this out at first, you can write little definitions next to it. So neutral meaning the number of protons equals the number of electrons. So if we start out here with phosphorus, we've got the atomic number right here in the isotopic notation. So this is part memorization. So if you look in the lower left, you'll see the atomic number is 15. And what really is the atomic number, right? We're always referring to the number of protons when we're talking about the atomic number. So the number of protons here is 15. Now we've got the mass number. The mass number in this scenario can be pulled from one of 2 places. So we have the mass number in the top left corner of this isotopic notation box. So it's 32, but also in this isotope format, which we may not have talked about as much before. This 32 or this 90 in the next, and strontium in the next problem, those are both referring to mass. So in these, if you know the notation, you automatically know that the mass is 32 atomic mass units. The number of electrons, we know that all atoms in this scenario are considered to be neutral. So the number of protons equals the number of electrons. So we got 15 protons, we have 15 electrons. Now neutrons, this is where you have to think about it a little bit. So if you recall, mass number, so maybe if I write this in the box here, mass number equals the number of protons plus the number of neutrons. So based on that, if we have a mass number of 32 and we need to subtract the number of protons, or 15, that leaves us with 17, right? So the number of neutrons ends up being 17. Just to center those. And so what I would like you to do to earn the rest of your participation points is to use what you know and fill in the rest of this table. And the answers will eventually be posted in D2L so you can check yourself. But I will continue on with you in these next couple questions. So the element magnesium exists as 3 naturally occurring isotopes. So we've got magnesium with a mass of 24, 25, and 26. And so isotopes have pretty similar chemical properties. So although these 3 isotopes of magnesium will have virtually the same chemical properties, there's differences in the composition of their atoms. The first question, just very straightforward, what subatomic particles differ between isotopes? So remember, whenever we're talking about isotopes, we're talking about a deviation in the mass. And when we talk about mass, your first instinct should be neutrons. So we can say these 3 isotopes differ in the amount of neutrons they have. And they want to know by how much. So we know that 1 neutron is approximately 1 mass unit, right? So magnesium 26, being that it weighs 26, would have 2 more neutrons than Mg 24 and 1 more neutron than Mg 25. So that's just by looking at the mass number next to each of them, doing a little subtraction. So that is A. B, what subatomic particles, some spell check here. What subatomic particles would be the same for these 3 isotopes? So they're all magnesium, right? So it's the same core identity. And when you think about the identity of an element, you're really thinking about the number of protons, right? You're thinking about the atomic number. So the number of protons would be the same. And because these are really just differing in the mass, right? The other subatomic particle, electrons, we consider to have 0 mass, right? So usually there's no difference in isotopes amongst the number of electrons that they have. The number of protons and electrons would be the same. So if you'll remember, when we start to add and subtract electrons, that's when we're talking about ions instead of isotopes. It's very easy to get them confused because they both start with an I. For these isotopes, list if the following characteristics would be the same or different. So the mass number is different, right? In this notation, these 24, 25, and 26 are referring to the mass. So So those would be different because they have a different number of neutrons. The atomic number is the number of protons, and those are all representing the identity of the atom. And magnesium, these are all magnesium isotopes. So the atomic number is the same. The atomic charge. So we stated in the above answer that the number of protons and electrons would be the same for these three isotopes. Which one is dealing with charge? That would be electrons. Electrons determine if there's a positive or negative charge. So because we say they have the same number of electrons, we're saying that the atomic charge is the same. So now moving on to the next set of questions. So the previous examples of isotopes all involve neutral atoms. So we're talking about atoms that do not have a charge. They have a charge of 0. However, as we mentioned earlier in class, when elements undergo chemical changes, they sometimes lose some of their electrons or gain extra electrons. That's what allows them to participate in chemical bonding. So their charge will sometimes change, so they have higher affinity to certain atoms. Now they're saying here the number of protons and neutrons does not typically change in chemical reactions. So when the number of electrons in an atom does not match the number of protons, the atom is called an ion, and it will have a net electrical charge. And these questions are really trying to hit at what we know about ions now instead of isotopes. So when an atom loses electrons, what kind of charge will the ion have, positive or negative? How do you know this? So first off, what do we know about electrons? If you remember from that chart in the above notes, we say that electrons have a -1 charge. So the more electrons you have, the greater sum of negative charge you have. So if you are losing a negative charge, are you becoming more negative or more positive? You're becoming more positive, right? So losing an electron results in a greater positive charge. We know this because electrons are a subunit of negative charge. And if this is difficult to think about initially, you can think about debt. Debt is a good analogy. So if you are in debt, you have a negative amount of net worth, right? But say your loans get forgiven, say you lose that negative aspect of your wealth, you would essentially be getting closer to 0 or positive, right? So that's the same exact thing here with electrons. Now for B, when an atom gains electrons, what kind of charge will the ion have, positive or negative? So if you are in more debt, if you are in debt and you take on more loans and you accumulate more debt, are you more negative or more positive? More negative, right? Oh, cutting down to the next page here. When an atom gains electrons, the charge of the ion becomes more negative. We know this because we are gaining subunits with a negative charge. So now I'm going to do the first section of this table here. And this is similar to the exercise we completed above. However, this time we do have that charge symbol in the isotopic notation. And you're basically going to be just, again, using part of the puzzle to fill in the rest of this. So the atomic number, we've got zinc here. We know that the atomic number in isotopic notation is always in the lower left, and we know that the mass number is in the top left. And here we have a net charge of +2. So the atomic number here we know is going to be 30 because it's right here in the notation. For the mass number here, we got 58, also from the notation. Now the number of electrons. So if we think about the net charge, if we're thinking about the number of protons minus the number of electrons, so here we're going to try to total up what the net charge is. So if this was a charge of 0, we would have 30 electrons, right? However, the net charge is +2. So we could probably, in that case, only have 28 electrons, right? Because if you are losing electrons, you're becoming more positive. So you're losing 2 electrons, and that's what results in this +2 charge. So now for the number of neutrons. So we know the number of neutrons is the mass number minus the atomic number, right? So the number of neutrons here is 28. And the number of protons, we know that the number of protons is synonymous with the atomic number, and that is 30. So we know that this is 30. So take a shot at the rest of this table, and you will eventually have access to the answers, and I will use this to gauge your participation for the day. And if you have any questions whatsoever, please don't hesitate to reach out. Thanks.